Let's take a look at some examples to illustrate differentiable functions. Remember that a function is differentiable at a point if the derivative at a point exists, which graphically speaking means that only one tangent can be drawn at that point. Algebraically, it means that the tangent drawn must have a slope of measurable value. Similarly, we're going to say that a function is differentiable on an interval if it is differentiable at every number in the interval. Let's start off with the first example. Here we have the function gt equals t over t plus 1. That's a rational function. And we have to discover at what points this function is non-differentiable and explain why. Now, to discuss differentiability, we need to find the derivative of a function, and obviously, we are using the first principles formula here because we do not know specific formula, we haven't learned one yet, for the derivative of rational functions. So that means that we're finding the limit as h approaches 0 of g at t plus h minus g of t divided by h. That will give us the derivative at any point t. So substitute or bring g of t in the equation of the derivative, which means that I'm going to draw a long fraction here. Instead of t, now we have to write t plus h, which means this t here will become a t plus h, and this t is t plus h. So the function g of t plus h would be t plus h over t plus h, and then obviously we have plus 1 there as well. And then minus gt. gt is t over t plus 1, and then divided by h. So next we'll try to simplify this expression as much as we can. And for this, we are going to simplify the two fractions or subtract the two fractions or rational expressions. We have the limit as h approaches 0. We have long fraction. As you can see here, the denominators are different. So what we're going to do next is make the denominators the same. So for this, we'll have to multiply by t plus 1, both numerator and denominator in the first rational expression. And we'll multiply by t plus h plus 1, both numerator and denominator in the second rational expression. So let's see what this is going to look like. So we're going to bring both rational terms or rational expressions under the same denominator. Remember that the denominator should be in factored form, so do not expand. T plus 1. And the numerator in simplified form will be t squared plus t squared plus t. And then we have ht plus h. So plus ht plus h. Next, we have minus t, multiplying every term inside the brackets. Attach the negative sign to the numerator. It makes it easier to simplify. So that would be negative t squared. So minus t squared. And then minus t times h minus th. And then minus t times 1 is minus t. Denominator h. Now let's see what we can simplify here. This is the fun step. So you see that t squared and negative t squared will add to 0. Negative t and positive t also add to 0. And notice that here we have ht and negative th, like terms, they add to 0 as well. So let's rewrite the limit one more time in a more simplified form. And you see that the numerator will be just h, denominator t plus h plus 1 times t plus 1 over h. Now it's time to divide by h. So I'll make this red. Remember that division by a fraction means that you're multiplying by its reciprocal. So I'll continue this simplification right here, exactly where we're at. That would be the limit as h approaches 0 of h over, so here we have t plus h plus 1 times t plus 1, and then we said division turns into multiplication, and that will flip the denominator, so from h over 1 to 1 over h. And again, the fun step, simplifying. So we'll say that g prime t equals the limit as h approaches 0, we're almost there, of 1 over t plus h plus 1 times t plus 1. We have simplified the expression inside the limit completely, which means that we are ready to substitute h by 0. So we have 1 over t plus 0 plus 1 is t plus 1. And then times t plus 1. So therefore, we're going to say that g prime t would equal 1 over t plus 1 squared. So as you can see, the derivative of a function is a function on its own, and in our case, it is a rational function. So the function is gt equals t over t plus 1, and the derivative of it at any point t would be 1 over t plus 1 squared. Now, algebraically speaking, I want us to think, is this expression defined for any real value of t? As you can see here, we have restrictions in the denominator. So t plus 1 has to be different than 0, which means that t must be different than negative 1. So what that means is that g prime is undefined at t equals negative 1, because substituting negative 1 into the derivative equation will make this expression or this equation undefined. We'll give it an undefined value. So therefore, we're going to say that this function is non-differentiable, or we cannot find the value of the derivative at t equals negative 1. So graphically speaking, what does this look like? So what I did in here was draw the graph of the function gt. So the function gt will have the vertical asymptote at t equals negative 1. As you can see here, we have t plus 1 different than 0, which means t is different than negative 1, which means that there is a vertical asymptote at t equals negative 1. And as you can see again, a horizontal asymptote will happen at y equals 1. That's because numerator and denominator are of the same degree, which makes the horizontal asymptote y equals 1. So the horizontal asymptote y equals 1. And the vertical asymptote will be right here at t equals negative 1. So we are going to say that in this particular function at t equals negative 1, where I am unable to draw the tangent line because the function is undefined, so there is no point where a straight line can touch the graph tangibly. So therefore, we're going to say that the function is non-differentiable at that point, and that's how you explain it graphically. Now let's move on to the next example. This time we are looking at the function rx equals square root of 5x minus 8. We want to find at what intervals is the function non-differentiable, at what intervals is differentiable, and explain why. In other words, we'll discuss the differentiability of it. So we'll start off by finding the derivative. So for function rx, the derivative will be r prime x, which is the limit as h approaches 0 of r at x plus h minus rx divided by h. So that equals the limit as h approaches 0 of long fraction line. We'll have the square root of 5 instead of x. We're going to write x plus h, and then minus 8. Minus the square root of 5x minus 8 divided by h. I'll have to make this a bit smaller. Okay, let's zoom in. And there we go. We have now the limit as h approaches 0. We'll write this in a slightly more simplified form. And big fraction, square root. So here we go. We have 5x plus 5h minus 8 minus square root of 5x minus 8 divided by h. Now, obviously, we see here that h cannot be substituted by 0 because that's undefined. It's an indeterminate form limit. So we go the limit as h approaches 0. And in order to eliminate h, we need to get an h as a factor in the numerator. Because h is hiding inside the square roots, to get it out, we need to remove the square roots. And we have learned this before. We have to do this by performing a conjugation on the numerator. So we are multiplying by the conjugate of the numerator, which is 5x plus 5h minus 8. So remember, this would be the exact same thing. Instead of minus, we'll have a plus, the square root of 5x minus 8. And then we are going to multiply the numerator by the exact same binomial. So divide by 5x plus 5h minus 8 inside square roots plus 5x minus 8. Now, let's simplify. So we have 5x plus 5h minus 8 minus 5x minus 8 divided by h, and then multiplied by the conjugate. Now, remember that these two together will multiply to give the difference of squares, so which means that the square roots will be squared, so they will disappear magically. Always magically, because math is magic. Here we go. Limit as h approaches 0. We'll simplify. So what we have in the denominator is the h. We're not changing the denominator at all, so we're going to leave it as is for a couple of steps at least. And we are going to change the, here we go. We are going to simplify the numerator. So hopefully we are going to see the h as a common factor. Let's see what happens. Here we go. We have 5x plus 5h minus 8 minus 5x and then plus 8. So let's see. We get 5x and minus 5x, negative 8, positive 8. So notice that we ended up with h as a common factor here. So h and h will simplify. So I'm going to show this in one more step in case you don't see it very clearly here. So the limit as h approaches 0 of 5h divided by that entire denominator. So we can now chop. So that would be the limit as h approaches 0 of big fraction. Let's paste this one more time here. And in the numerator, we're going to have just number 5. So now we're ready to substitute h by 0. So that will make 5 over. And here we go. We have the square root of 5x minus 8. Remember, h0 will make this term 0. And then plus the square root of 5x minus 8. So we're going to say that the derivative of function r would be 5 over, notice how here we have two same square roots. So we will combine them, they're like terms, 2 root 5x minus 8. Now I want us to think, algebraically speaking, where is this function, which represents, by the way, the derivative of function r, where is it undefined? So as you can see, this is a rational function and it will be most probably undefined at the restrictions if there is any. So we're going to say that the restrictions here are that 5x minus 8 cannot be 0, obviously, because that cannot be 0, but also We want 5x minus 8 to be positive. So if 5x minus 8 is negative, the square root doesn't exist. So what that means is that 5x has to be bigger than 8 or x bigger than 8 over 5. Remember, bigger than but not equal to 0 because we don't want the denominator 0. So we'll say that the value of Rx, R prime x, exists if x is bigger than 8 over 5. So I'll write this down. R prime x exists, or it has the domain for x values bigger than 8 over 5. So we're going to say the derivative exists in this domain. So we're going to say that the function Rx is differentiable, or will have the derivative evaluatable for x values bigger than 8 over 5. So the question was asking to find the intervals where the function is differentiable, and that's how we determine this algebraically. Now, graphically speaking, the graph of 5x minus 8 will be the square root of 5x minus 8 over 5, which means that the function will start at 8 over 5, and then there will be some horizontal compression 5 times, and this will be the graph of the function itself. So as you can see, at exactly 8 over 5, which is the starting point on the graph, if you were to draw the tangent line will be a vertical line. So the slope of a vertical line is undefined, and that's what we actually obtained from the algebraic solution. So the derivative was also undefined at 8 over 5. And the reason why, and we are making the connection here with the graph, is because that, yes, we can draw a tangent, but the tangent has an undefined slope. So therefore, we're going to say that the function Rx is differentiable only for x values greater than 8 over 5. You can draw the tangents at any point where x is bigger than 8 over 5. I hope this made sense, and I hope that this helped you better understand how differentiability works, and most importantly, the connection between algebraic and graphical explanation of the differentiability of a function. Thank you for watching, and bye for now.